Okay, so uh, so I'm going to continue the discussion of layering today, right? And I want to discuss this one classic paper, which is it's a very old paper. It's one of those design argument papers, which was arguing for how you can organize the network functionality better. So I'll also discuss that paper today. So before that, quick announcement. The office hours for the TA it'll be on Tuesday and Thursday between like 1 and 2 p.m. So I believe that he will also post this information in Piazza. So you should be able to see that. So that way you guys have an office hour every day except Friday, right? There is an office hour every day. So as you know, probably the first programming assignment will be released after the break, like after the Labor Day, the Wednesday after that. So and then I think you guys will probably have to go to TA for some of those things too. If you have any questions about the assignment. So that's a quick announcement. So what I want to do is I've also posted the lecture capture on the slides in Piazza. There's some issue with the mic. Okay, I don't know if it's because I'm walking away or because my laptop's mic noise cancellation is not perfect. So I tried to fiddle with that for this class. We'll see how that works. And also from the next class, most probably I will ask these guys to enable the lecture capture in the room, right? Your traditional Blackboard thing. I hate Blackboard, but we'll see how that goes. I think that this is better, but we'll see.
Well, like, what are your release dates for the slides? Are you going to be after you cover the slides? Are you going to release them? Or?
That's what I'm doing simply because I sort of edit them before the class, depending on, oh, okay, in the last time when I taught this is one part I wanted to emphasize, things like that. If you want, I can post it before and then repost it after. Override it.
I was just wondering, but
I could do that.
someone else can decide.
That's fine. So I'll do that. I think this is something that I think helps students. So I will post it before. So continuing from the last class, we were talking about the network layers, right? So there's different kind of functions that the network provides, like addressing, routing, flow control, security, right? And the question that we were asking is how should they be organized, and how should they interact? Meaning, should there be any dependence between them? So to answer that question, right? So we talked about how you can sort of independently structure the different network functions into layers so that one layer is taking care of a specific set of functions, right? For example, security could be an application layer functionality and addressing could be a network layer functionality, right? So then you have built a hierarchy, right, of layers, and each of these layers, each of them is taking care of a few functions, right? So now you have this problem that when the layers have to talk to each other, right? So for example, if you're writing an application, right, and you're sending a video file, and then some layer has to come in and attach information about addressing. For example, let's say the network layer is providing the addressing functionality. It needs to attach relevant information to the message as the message is going out, right? So that on the other end, when the message is received, somebody who needs to do routing can actually look up this information and send the packet correctly. So there is a notion of encapsulation. So any message that any layer is sort of handling has sort of the actual data or raw data that the layer doesn't really care about, right? And there is the header, right? So data is basically what the sender wants the receiver to know, and the header is basically the stuff that this particular layer, whatever layer it may be, it's going to use that header information to provide you some sort of service, right? So if you're talking about a layer that provides addressing, right, then you might have a source and destination address, right, and you might need to know other things like you might add some redundant information like error control stuff. So if the data got corrupted on the way, you can figure it out, like CRC, cyclic redundancy checks, right, or error correcting codes or anything, any extra encoding stuff. So this is usually also referred as metadata. So metadata header. So any layer sort of deals with any layer takes data that is being sent to it, right, and then attaches its own header, which is the stuff that the receiver will sort of use for providing some functionality. We'll talk about concrete examples here. So let's go back to sort of very simple example, right? Let's say Lisa wants to send some message to Jay, and then the message is Roger Federer is the greatest, right? And then if you're talking about in this case, the header basically is a very simple post-it communication. The header will be simply like the sender and the receiver. In this case, Lisa and Jay. And in this case, the protocol format is very simple, right? The message format has this common to address and the message contents, right? And this is a very simple way of communicating. Let's say you can post it on your fridge. But let's say you want to sort of not post it on your fridge, but you want to send it by your USPS or mail. Then you'll have to put that thing in an envelope, and then you'll have to write the address, right? So what I'm getting at here is that if your communication channel, right, if your communicating layer is by posting it on the refrigerator, your header is simple. It basically says it's sent by Lisa and sent to Jay. But if you're sending it through USPS, the header is basically your complete postal address, in this case, the blue residence, right? And blah, 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 whatnot. So the same analogy holds, right, in the network layering. So when you're talking about application layer versus transport layer versus network layer, each layer attaches its own header. So layering is basically separation of functions, right? So in this particular example, we actually, in this sort of toy example, we have two layers. The bottom layer, the lower layer, right, is basically your mailing system, right, which is contained inside the envelope, which is contained outside the envelope itself. And then the actual message, right, itself is coming from the post-it, right? So you have sort of the postal system, which is delivering the physical mail, and then you have the post-it note itself, and each has its own header, right? So the nice thing in this toy example, or in general in the network layers, is that there is sort of a clear separation of responsibilities, right? So if you're talking about the sender and receiver of this simple post-it note, they don't have to know how this message is being delivered. Maybe it's delivered by USPS, maybe it's delivered by FedEx, maybe it's delivered by UPS, maybe it's delivered with with a pigeon. It doesn't care. For all like they don't have to care, right? So there's complete independence, right? And similarly, like if you go to the lower layers, like the USPS guys, they don't have to really care whether Lisa's sending it to Jay or whatever. So long as the address is kosher, everything works. So the same sort of analogy holds. So I will sort of go to the internet's layering model. So we talked about this 4-layer model, which has this application layer at the top, right? It could be email, it could be file transfer application, FTP, and then you have the transport layer below it, right? Which actually deals with end-to-end connections. And then you have the network layer where you have sort of the global addressing and naming, right? And then you have the link layer, the data link layer, which actually deals with delivering frames of data over a physical link. Could be a copper wire, it could be a fiber optic cable, it could be a 4G LTE link, wireless link, it could be a Wi-Fi link, it could be a WiMAX link, it could be a satellite link, doesn't matter. But the link layer is what that needs to take care of this. And then at the very lower end, you have actually the physical layer, which we don't have to care for. It's not interesting to us, right? So from the application's point of view, right, the programs and the programmers, they interact with the network. They use the socket API, right? I will talk more about socket API. There is an assignment using that. But in general, you're talking about simple library functions like send and receive, right? So from the application's point of view, I'm just going to use this library and write my programs using sends and receives, right? And then application layer protocols can be defined for specific use cases, right? By choosing what type of layers protocols are appropriate for the application in hand, right? For example, let's say when you talk about HTTP protocol, which is predominantly for delivering web pages, it needs to be reliable, right? For example, you are fetching UIC's homepage from some web server. Something got corrupted. That's not okay. Your browser is going to it's not going to display. It's not going to render the page properly. So you need reliability, right? So when you're designing an application layer protocol which requires reliability, then you will choose a transport protocol that provides you reliability, because reliability is basically provided by the transport layer. So this is where the choice matters. So when you design an application layer protocol, you have to pick the right transport layer protocol to use depending on the application. Any questions? We briefly sort of touched some of these things in the last class, and some of these things will become clear also as I go along. So now let's sort of step one layer down. So when we go to the transport layer, now you're actually talking about the transport layer from its point of view, it's seeing two processes, operating system processes running on different computers, exchanging bytes. That's what it sees. It doesn't see an email. It doesn't see a web page, right? Because it's blind. It's a lower layer. So when it gets data, all it's seeing is that it's seeing a sequence of bytes being transferred between two processes running on two different machines, probably across two different continents. But that's all it sees, right? So what is its main goal, right? So what is its key responsibility? One of its key responsibility is to multiplex different messages that are coming into its interface, network interface, in multiplex and demultiplex messages to different operating system processes. Maybe in your computer, you are also watching a YouTube video, and also you're browsing some web pages. So the data is all multiplexed and coming in, and somebody has to sort of demultiplex this data to the two browser tabs that you have open, right? And that is ultimately under the hood is done by the transport protocols. So transport protocols actually have some sort of a mapping between different operating system processes that are running in your system, and that's the streams that are coming in. That's how it sort of can multiplex and demultiplex. So not only that, obviously any layer has to decide on the exact APIs that it wants to expose. So when I talk about an send API, it needs to sort of design what are all the arguments to this send call, right? What does it return? What does it take? And all that. So that's sort of generic for all layers. So another important responsibility of a transport layer is to manage the realities of the network. So what I mean by that are things like congestion, right, or loss. Maybe you are operating on a link that is not reliable, right? Maybe a satellite link or something, right? So parts of the packets are bound to be lost. So it is in that scenario, it is the job of the transport layer to make sure that it can be transmit or code or do whatever so that it can sort of provide a reliable service. All right. So now, going one layer further down, you hit the network layer, and here you're actually talking about you have a notion of a global network like the internet, right? And now, because transport, it is the network layer that has this global visibility, right? So it only at the network layer do you actually can see the entire internet as a map, right? And therefore, only in this layer can you plan the routes, right? So the routing is the key functionality at the network layer. So when I mean routing, what I mean is that how do you get a network packet to traverse from the source to destination, what paths to take, right, or what paths not to take. Uh, so for you to do routing, you have to sort of uniquely identify each point in the graph, or in other words, you need to figure out how to name or address, right, each device in the network, each node. So at the network layer, from its point of view, all it sees is a big graph, right? And it needs a way to sort of tag the nodes, address them. So how do you assign IP addresses, right? That is one of the key job of the network layer, right? So assigning IP addresses, right? Is it uh, in any graph, right? And if you want to sort of assign some IDs to graph, then there are many strategies to do it, right? Because the graph itself has a topological structure. So you'll have to sort of use the structure to assign the names, right? So which is just one of the key challenges when it comes to internet. Internet is also the structure is not set in stone. It's always changing. Things move, right? Particularly with mobility and all that. So there's a lot of challenges here, particularly over the last 2 decades. Mobility has become a big thing, right? So the IP addresses are not. You cannot associate IP addresses with a location. So basically, when you talk about your phone with IPv6 and all, like your most of the devices today, the location is usually you can probably find out the location using something like a MAC address, but not the IP address, right? So when you have mobility in play, then there's a lot more challenges here. And when you go to the further down to the link layer, you're actually talking about specific things related to the medium itself. See, up till the network layer, we didn't really care about the actual transmission medium, right? Whether it's a copper cable or whether it's wireless or whether it's satellite, we didn't care about it, right? But when you go to the link layer's primary goal is not global communication. It's just one step of the communication, one hop. How do you get a packet to go from one node to the next node over a medium, right? That so it needs to deal with the specific type of the media that you're working with, whether it's a copper cable or fiber optics or whatever. And then there is also there is a key question of media access control, which is when your medium itself is shared, right? When multiple entities want to use the medium, how are you going to sort of divide up the resource and allow everyone? So here there are many strategies, right? So you can have a central arbiter that actually tells the communicating parties, right, to communicate one by one. That's one dumb way, right? Or you can be more sophisticated. You can go You can have CDMA, right, where you can design codes that are themselves orthogonal. So you can sort of a fixed number of codes can be used together over a shared medium without conflict, right? So there are lot of choices here when it comes to how to share the medium. So so we talked about a lot of different layers, right, in the last class, and then we talked about like different examples of the protocols in each layer. So we talked about TCP and UDP. There are many choices in each layer, right? But then in one of the layers, right, you really cannot have a choice. I mean, I told you that, okay, once you organize the functionality in the layers, and then you can design protocols that provide a certain level of service. So depending on what type of service it provides, you can have different protocols in different layers, right? That's all true. But there's one layer where sort of you cannot have multiple protocols. If you have, then things won't work, which is that. Yeah? Reason? Reason. Why?
Oh, because it prevents accuracy, right? If people are using different accessing systems, you can't send it to the same.
Yeah. So network, the other way to say it is that it's global, right? It is the only layer that has to operate globally. And therefore, sort of everybody has to talk the same language. So it provides addressing and naming. So ultimately, like everybody has to talk the same language. So really, at the network layer, you really have only IP. Everybody has to talk the IP protocol for you to sort of have the internet. Right. So if you put all these things together, you have this nice sort of lot of choices at the higher layers, a lot of choices at the lower layers, and all converging to sort of IP in the middle. Right. You have this sort of thin waist protocol suite model. So where so this is all very logically clean, right? So at the top, depending on the application, you have different protocols: FTP for bulk file transfer, HTTP for browsing, right? And blah blah blah. So many other things. And then at the transport layer, depending on whether you want reliability or not, you have two choices. You have TCP when you want reliability, and if you don't want reliability, you have UDP. And then yeah.
So does the transport layer have two layers?
Sorry.
Does the transport layer have two layers? Because the TCP and UDP are transport protocols, and FTP, HTTP, those are also transport protocols, right?
Which is transport protocol? TCP and UDP are transport protocols.
Are FTP and HTTP?
They are application layer protocols. So there are 4 layers here.
Because like I thought HTTP stood for Hypertext Transfer Protocol.
Transfer.
Transfer.
Yeah.
Okay.
Yeah. So, so basically, from the top, right, depending on the diversity of applications, you have many choices. From the bottom, depending on the diversity of the media, you have many choices. Yep. The choices at the bottom, right, are simply because you have many different medium. The choice at the top is simply because you have many different applications, right? And it's the center where you sort of converges, all of them converge. Yeah. So essentially, in very short term, right, IPv6 is backward compatible with IPv4, and therefore it's all yeah. In other words, they can understand each other. The other short explanation for that is that the only difference, the high level difference going to IPv6 from IPv4, the reason for going from IPv6 from IPv4 is that you just wanted to support a lot of hosts, so you just expanded the address space. That's all you did. Oh, this is annoying. So, so we briefly talked about this example in the last class, right? Let's say you're transferring a file from node A to node B. What's involved, right? Let's go through that again with this new knowledge. So from the application point of view, right, the things that it cares about are things like, okay, how do you authenticate a client, and how do you ensure that it has permission to access the file, and also exception handling. What if the file that you're asking for is not available, right? And things like encryption, should it be confidential, things like that. And if you go to the network layer, then you have this question of how do you identify an address, which routers, like how do you do routing, how to ensure reliable in-hour delivery is probably not a network. I mean, at a very high level, it's not a network layer question, but it's a job of the network. And then also how do you actually get all these things to work? Even if you pick a path, right? The packets have to honor the path. How do you make them follow it? So obviously the network, that's why it's organized into layers. We went through this, and then I'm just going to skip. So basically, for academic purposes, right? People defined this 7-layer model protocol stack, the ISO layer, which is never implemented, never used. So I'm just going to, it's not important, okay? In practice, you're really dealing with 5-layer TCP stack, with the 5th layer being physical layer, which also we don't care. So really, we care about the 4 layers from application, transport network, and link layer. So, and also another thing is that of these 5 layers, the design was,
Why did they dump 7 layer? Like, what made it attractive?
No, because they actually never designed it. It's almost like an afterthought. So they designed it with 5 layers, right? And then people came, oh, it'll be so nice to have 7 layers. By the time the thing has already taken off, right? So it was something like a useless exercise, to be frank.
So do we say that 5 layers is TCP/IP layers?
Yeah, it is called as the TCP/IP stack. So also another thing is that it is possible for you to say that all devices have to implement all these layers, but the guys behind internet, behind the design of this, they were smarter than that. So they wanted the whole design of the internet, right, predates VLSI. It predates very large scale transistor integration. There was no, when internet was like taking off, there were transistors, but there were no ICs, integrated circuits, right? So if you look at the way silicon technology has improved, there was transistors, there was ICs, there was large scale integration, and there was very large scale integration, right? So there was no integration at that point. So it was so they had to make these routers really, really simple, right? And the higher layers are implementing much more richer functionality, right? So they didn't want to overburden the routers, right? So they designed it in such a way that the routers are the in-between points that are responsible for only forwarding these messages. They only implemented sort of the bottom 3 layers. And the end host was implementing all the 5 layers. So that's why, for example, like why the bottom 3 layers? Because they're dealing with low layer functionality. So if you're talking about data link layer, its main job is to transfer frames over a link, right? So it has to do very low level things. It cannot get away from it. So if the router has to do forwarding, it has to understand what the sequence of bits actually mean. And basically link layer is actually doing that. When does the frame start? When does the frame end, right? And how to extract the address from the frame. Those are the low level things that link layer does. And also oftentimes the link layer stuff is implemented in hardware. So the link layer is implemented as part of your NIC in your laptop. NIC and probably some part of that in your device drivers, but that's about it. Whereas, I mean, network layer, obviously we talked about it. I think we briefly talked about the delivery model also, that IP, because they wanted the whole design to take off, and they wanted everyone to understand and speak IP, which means that IP cannot be really complex. And because of that, the delivery model is basically a best effort. God, this is horrible. This is just a best effort delivery model. So you want a packet, right? The packet could be lost, reordered, delayed. It doesn't give you any guarantees. Which means, what is the implication of that? Does it mean you cannot have reliability? Sorry? Yeah.
Well, I mean, you have TCP implemented over IP, so it's possible to create a reliable framework.
So that's the thing. So if you want, you can implement a lot of these low-level functionalities at the higher layers. Right? It will just not be fast. So, for example, so that's what you're right. That's what they did. But the implication of that is that, let's say you are sending a file from point A to point B, right? And the path has to go through like 100 devices, right? Between device 50 and 51, some one bit got lost, right, or corrupted. Now you'll have to sort of redo the send from the sender to the receiver. So you gave up a lot of actually performance for simplicity. Yeah.
What I was thinking is like the layer 2 or like the data link layer will it works on the protocol like TCP, and like transport layer will take care of whether it's being sent properly or not, like whether any data is dropped, like any data from packet is dropped or not. So like the lower layers should not be worried about like whether the packet whether any data is being missing or not, because like suppose it's sending from host 1 to host 2, and in the middle it goes through 15 or 20 routers or switches. So this routers or switches should not be worried about whether the data is being dropped. When it reaches host 2, then
So it is not a question of should or should not be. So long as you can do things at the end host, you can make it work. But that may not be the most efficient way to do it. If they can, for example, do any sort of, they can provide any reliability at the lower layer, then things will be more efficient. But it will also mean that things will be complex. So the point I'm getting at is that if the internet were to be redesigned today from scratch, probably a lot of these choices will change. Because today, silicon technology is cheap. You can do reliability in these devices. Those are cheap. Like they won't even cost $1 to add these functions. So I think I'm going to skip it. We talked about this. So I'm just going to go to. Oh, this is really. Okay. So both TCP and UDP, the transport protocol options, right? They sit on top of IP. The key difference being that one of them is reliable, the other one is not. And because it is reliable, it also comes with its own overheads. Because it's reliable, it needs to sort of establish the connection, and do a lot of housekeeping. So as to make it reliable, right? That's the very sort of high-level difference. Also, the natural implication of that is the latencies may be higher with TCP than UDP. So depending on the type of application that you are dealing with, you probably can choose one or the other. The application layer is basically deals with the details of application. In this figure, I've also listed some options. Those are not really options. Okay, so a lot of these protocols that are listed there, they provide part of the network functionality. So they're not really options per se. They all have to be present. For example, IP should be present because without IP, you cannot actually forward the packets from one end of the globe to the other end. ICMP is basically a protocol for reporting errors. If one of your router does something that it should not, ICMP is the protocol that you can use to debug it. OSPF and REP are basically routing protocols. I will talk about routing exhaustively in this class, but at a very high level, they are used to establish. They are protocols using which the routers can learn about the nature of the graph itself, and after which they can forward. So without RIP or OSPF, IP cannot work. And BGP is also a routing protocol at a very higher level. We'll talk about that. Yeah.
If you were trying to like develop a network that isn't supposed to necessarily be in communication with the entire internet, right? Like you're doing some sort of like internal network, like on in a building that you own or something like that, and you're just trying to develop your own connected component. Would that open you up to using like sort of different options in the network layer besides IP, because you're not necessarily expecting to be sending your data externally?
So first of all, you don't even have to use IP, by the way. You can use your own, right? Because now you have the complete, it's a blank slate, right? But if you're using IP, you can use your own work. So you have to use some routing protocol. Okay, you don't have to use OSPF. You don't have to use JET. You don't have to use BGP. In fact, some of these companies like Cisco, they provide their own routing protocol if you want to use for networking sites. So you can use anything. There are many options, right? And as I said, even IP is not needed because you're starting with one side. And also, you really don't also have to use routers, right? Because you can actually buy an expensive server that has multiple network interfaces, and you can use that server as a router, just that it will be doing routing in software. So what a server will do is that it will read data streams coming from one network interface, right, and process them and figure out where to send them to. You just need a server with multiple interfaces. So if you're doing software routing, then again, you have like 360-degree freedom. You can do whatever you want, except that, you can't go up to 40 gigs. I mean, you can't go to really high speeds. So there, the protocol, the TCP/IP protocol stack put together. So if you're actually two hosts are communicating, the hosts have to implement all the layers. In this case, let's say you're talking about a web server and a web client. So you have a TCP, you have the HTTP, TCP, IP, and the Ethernet on the sender and the receiver. And in between, they're going through a bunch of routers. The actual link between these hosts and the routers, and also among the routers, right? Between the routers, there can be any, right? In this case, you have Ethernet and SONET link. It can be anything. It can be any technology, right? So there you have the link layer where you have the diverse set of the link technologies, right? And then you have application, which is talking HTTP, right? And then you have the other transport and network layers. So also one other point that I want to emphasize is if you are sending, let's say you are talking to some other computer within UIC, right? And both of you are actually in the same domain, Ethernet. Then really the packets, right, will not even they will not even cross. So basically, on the sender, you will send it through your sending interface. and then the link layer will actually take care of completely sending the packet all the way to the destination, because you're all within the same technology, same domain, right? So the actual IP-based forwarding will only kick in if you have to cross, if you have to go across a different link layer technology. Like, for example, you're transitioning from wireless to wired, right? Or you're transitioning from UIC network to some other network, let's say Stanford. Then, at that point, you will cross over to IP and you'll do IP forwarding. Yeah.
So when you send a packet from a network layer to the link layer, like does the host determine which bounce it'll take, like which hops it'll take, or is it just like it knows where to send it for the first hop, and the first hop sends the second hop, and the second hop decides how to get it?
What do you think? Why? I mean, that's a correct answer. No, I'm trying to figure out your reasoning. So that's a correct answer. It will send it. It will not know the complete path. It only knows the next hop.
Like, I'm just wondering how they not maybe it'll just bounce back and forth forever.
Oh, that can happen. But there are protocols that will detect if such loops exist. So basically, instead of always designing something that is correct, it's something that designed to work correctly in the most cases, and then catch these exceptions. So basically, if you were to know the full path, right, it is impossible, because the internet itself may have tens of billions of nodes, right? So every computer, it's impossible to know every other computer and the path to the computer. The complexity is simply overwhelming. So it's simply not doable. So the best it can do is that, given a destination, whom should I send it to next? That's all I know. And that's all it knows. And if there are loops, like packets coming back and forth, they actually detect it. They detect the loop, and then, that means your routing is broken if something like that happens. Yeah.
You said on the subnet you can actually just use a link layer to communicate with the other host directly.
Only if you're in the same domain and same technology. Like if you're on Ethernet, let's say you are talking to somebody over you're in the lab connected through a wired LAN, and you're chatting with somebody. Yeah.
What happens if you have like a virtual host on your machine? Are you still going to go through all of the onion layers, so to speak, to talk to that virtual host on your machine, or like do you just skip all that and go, I don't know, like right through the just application transport on the same machine?
So the short answer to that is that you actually the stack on your guest OS and the hypervisor know what you're doing, and it knows the interfaces. So it'll just cut through all that. Although depending on the type of hypervisor that you're using, sometimes it might also be dumb. The very old ones like Zen and all. So this I've already answered. I mean, there are the routers only need the network link and physical, so that is easy. So this is also another thing, right? There's an interesting thing, encapsulation, that happens as data is flowing. So if you go back to this figure, right, as the data is going from the sender, right, sort of information is getting added more and more as the data gets passed from the application layer down to the transport layer. The transport layer attaches its own information, and then when the data gets passed to the IP layer, the IP layer attaches its own information, and so on and so forth. And on the receiver side, the same thing happens. You sort of, each bottom layer, right, removes stuff and then passes the data up. So there is encapsulation and de-encapsulation happening as the data goes through these layers, right? So basically, you have the application, right, and then you have the transport layer, which is adding TCP header with the data, and then there's a network layer, which is sort of adding the network header, and then there's the link layer, which is adding the link header. So basically, what is the data for a layer is is basically the header and data for the layer above, and so on and so forth. So the message sort of gets bigger as it gets passed down to the lower layers, right? And it sort of gets ripped off as it passes up on the receive side. So basically, then things become very simple, right? So we have sort of divided up the responsibility, so things become really simple. So if you want to design or write an application layer protocol, if you want to design an application layer protocol, you have to decide what is the transport layer protocol that you want to use, because you're sending it down one layer, and you design your application, right? Depending on however, maybe you want to design it multi-threaded, whether maybe you want to design it event-based, asynchronous programming, whatever you want, right? And then you implement it with the socket API. And then if you want to simply use the protocol, the steps are pretty much the same, right? You just have to choose the end host that you want to contact, right? And then you just have to sort of follow the APIs of the protocol. My God, this is annoying. This is why I hate to use this. So the key concepts here are the notion of service, interface, and protocol, right? Service actually answers the question what the layer provides. The interface actually tells you how to get that service, right? What is the semantics of the API? And the protocol actually is the details, is actually how the layer is implemented. So if you're designing the protocol, then you have to know the actual message format, what happens when a series of events happen, and it's much more detailed. But if you want to simply use it, all you have to know is actually the API, the interface. So, we talked about this, so I'm not going to spend time on these things. So this is one thing I want to focus, that is, this is one of the key things, right? The benefits of layering. So you have a lot of applications and you have a lot of different transmission media, right? If you did not have sort of a one common IP layer, the other problem is that whenever you want to add a new technology, right, it needs to interface with so many other applications. And whenever you want to add an application, the application needs to work with so many different types of media. So the complexity is multiplicative, right? But with layering, the complexity is linear. So whenever you want to add, you sort of add a media. So long as you know the interface to IP, you're cool. And similarly on the higher layers, if you want to add an application level protocol, all you have to know is how do you access the interface to IP, right? So basically this intermediate layer, right, in this case IP, provides sort of a single abstraction for various network technologies, right, and also various applications at the top. So this is yet another example of use of one level of indirection in computer science to solve a lot of problems, right? Like in virtual memory, we've used the same idea, one level of indirection. Like with virtual memory, like we have a limited physical memory, but we want to provide an illusion of unlimited physical memory. So what do? We have these page tables, nested page tables, and sort of we swap in and swap out, right? And using the one level of indirection, we provide the illusion of an unlimited physical memory. The same idea. So using a level of indirection through the IP layer, we have provided this illusion that sort of, even though there's a number of media and a number of applications, it all seem to sort of talk the same language. So here, I mean, what I was trying to get at is that, so let me try to think of a better analogy. I mean, how do we achieve platform independence with Java? Who can tell me? You have a JVM, right? So what does the JVM give you in Java? So like before Java, right? what you do is that you take your high-level code, you compile it to a low-level machine code, and if the machine that you're running is an x86, it's a different code, right? It's a different byte code. If you're running an ARM, right, it's a different machine code. And this was completely crazy because now the binaries are not compatible at all because the binaries themselves are different machine codes. So how did we solve this with Java, and how did we achieve platform independence in this case? What we did was we compiled all of them to a universal bytecode, right? And then the JVM sort of, whenever you add a new platform, right, your JVM needs to sort of, during the runtime, it has to take the bytecode and translate. That's how you achieve the platform independence. So it is the same idea here in the networking. So by having sort of everybody talk IP, right, you have decoupled the evolution of media and the evolution of applications completely. So when you want to add new applications, you don't have to worry, oh, do I have to design my application differently for twisted copper wire versus wireless? And that's what I was trying to get at. So the very high level ideas are same. Any other questions? So also what is the protocol? So it's the goal of a protocol is to get a message from the sender to the receiver. So the protocol basically defines what is the message format, right, and what is the transfer procedure. And also by definition, you don't when you're designing a protocol, you want it to be sort of completely distributed, right, and sort of no central thread of control, and the sender and receiver are sort of completely asynchronous. In designing protocols, one thing also you'll notice that they are completely asynchronous. They don't share a notion of a global time that is synchronized. And the expectations are always expressed in terms of sequence of actions, right? So if you do X, then they are expressed as state machines, that the sender and receiver are sort of exchanging some messages, and they are in a specified set of states that are clearly defined, right? For example, the sender sends the starting of the message, and then it waits for the acknowledgement, right? And then after receiving the acknowledgement, it sends 512 bytes and then waits for the acknowledgement. That is a typical example of a protocol operation. So another advanced topic here is, so often we talk about encapsulation, right? That is, we talk about encapsulation where as the data gets passed down the layers, you're sort of tagging on extra information. So using the same idea of encapsulation, you can also do what is called as tunneling. That is, you can sort of take the entire packet, right, that you received from the lower layer and treat that as if it's an application payload, right, and then send it again through the layers. So I talked about this idea of building a router by using a PC as a router, right? So you can write your own programs to act as a router. And when you do that, what you'll be doing is that the data that you'll be receiving will be the raw data at the link layer, right? And you can actually treat that as a payload. And then you can sort of tag on extra layers on top of it, right? And then send it down. This is so. Have you guys heard of the onion routing of Tor? Right? Yeah. So onion routing basically uses the same idea of encapsulation or tunneling. Basically, what it does is that instead of the data going through a series of routers before reaching the destination, the data actually goes through a series of endpoints. So basically, in other words, it goes through a series of tunnels, so you cannot really pinpoint where it's coming from. That was the high-level idea. So we'll talk a little more about tunneling in probably like a couple of lectures. I'll get into the details a little bit more then. So one other thing that I want to discuss is that I have already put this paper in my webpage. So this is the paper I talked about. This is the paper which was making a case that most of the time you should try to place complex functionalities not in the routers but in the end hosts. And it was arguing why that might be a better design principle. So this is like one of the most influential papers about organizing network functionality, right? So I think after this class, you guys should go and read that paper. Okay, this is bad. I'm going to switch it off. I'm annoyed by it. God. Okay, so this is not like a perfectly. It's not proposing a bulletproof theorem. It's basically a position paper. So it does not state a fundamental truth or propose a new idea, but it's basically arguing what might be a good design principle. So one of the key responsibilities of a designer is to choose the boundary between different functions, right? And you need to create some design principles to sort of guide designers to make this choice. And this paper really precisely attempts to do that. So the paper's central argument is that any function, in this case function being routing is a function, encryption is a function, any network function can only be correctly and completely implemented only with the knowledge of the application that is running at the end hosts, right? And therefore, if you try to provide that functionality in the network, right, it will not be complete. It'll be incomplete. Sometimes an incomplete solution may be okay if it provides a higher performance, right? But this choice, but the designers have to really weigh the pros and cons of implementing something in the routers. So an example would be to do encryption, right? So why not the routers encrypt every packet that is going along the way? Somebody could say, oh, why not? Why not encrypt everything on the routers? You could do it, but maybe my application doesn't need encryption. It's a dumb application. I don't care about the data, right? Maybe it's somebody's tweets, right? I don't need to encrypt the damn tweet. So if you provide that encryption functionality in the network, it's an overkill, right? Every router has to support that functionality. It costs money and it's painful. And not only that, even if you encrypt, even if routers provide encryption, the end host might have to still encrypt and decrypt because something may happen in the last hop. So in this case, it's sort of clearly the cost-benefit analysis will tell you that it's probably not a good idea to do encryption on the network. So this is the paper makes this argument using a series of examples. So one of the examples it picks is the reliable file transfer. Let's say you're transferring a file from host A to host B, right? So from your operating system class, you know that a series of steps have to happen, right? The first operating system has to read the file from the disk, right? And it's to read it to the main memory, and then it has to do a DMA from the main memory onto the network interface, right? And then it has to go through a series of routers or blah blah blah, all the stuff. And then at the receiver, it has to do the reverse, right? The data just gets written into the operating system buffers, right? The NIC buffers to the OS, and then the NIC interrupts the system, and then it copies the data finally to the application, right? So there are a number of steps, even in a simple file transfer program, and many of these steps are not really concerned with actually the network. There's also steps happening inside, right? So basically, there are a number of things that can go wrong, right? There could be failures in the disk storage. There could be some bug in the file system software, right? That's corrupting. There could be random errors that happen in your main memory, and that is becoming common these days. A high energy particle can hit your main memory and can flip a few bits, right? That's why more and more you see a lot of ECC and stuff like that in your main memory. So a lot of things can go wrong, right? Uh, so uh, so then there are two ways to make this file transfer reliable. So the sort of a naive approach would be, oh, why can't I make each step in the process reliable? And then when you concatenate it, you will get reliability, right? So that's one solution. The other solution is, oh, I don't care about the individual step, right? I will just only do an end-to-end check, right? And when anything fails, I'll just retry. I'll keep retrying until I succeed. That's another approach to this problem, right? So in the second solution, you are not trying to sort of fix the individual step, right? The individual steps are as they are, but when the host B receives the data, what it does is that it copies, it reads the entire file that it received, and it calculates some checksum and sends it to A, and then A checks the checksums, receives checksum from B, and compares to its own computer checksum for the file. And if they disagree, then B simply A says, hey, the file transfer is not complete. I'll resend again, right? Otherwise, they go forward. So these are sort of two different solutions to the same problem of providing reliability, and anybody can see that 2 is reasonably low cost than 1. That is straightforward. But what is not straightforward is that the first solution is not complete, right? So even if you do step by step, the receiver has to do the final check anyway, because there could be something that can go wrong in the last step. Whereas the second solution is complete, right? For example, if there's a software bug, right, even if you make the individual steps reliable, your file transfer will still not complete. So solution 2 in this case is complete, right? So and it requires no need for changing any of the lower layers. So when you are adding reliability in each of these intermediate steps, what you're saying is that I am adding new functionality at lower layers. And that is not only an overkill in this particular example, but it's also not complete, right?
Is it really the case that you have no need for reliability from the lower layers? I mean, don't you need like
So that's why I said it's a very. So when they say there is no need, they are saying from the perspective of correctness, not from the perspective of performance, right? So there may be need for you to add stuff in the lower layers, absolutely. But the goal is always performance, it's not correctness.
Yeah.
For correctness, you still need an end-to-end solution that works as something to fall back on.
Yeah, because I mean, I'm just thinking of like, you have like an extreme case of like, you end up unplugging the Ethernet cable from one of the hosts, and now it can't send or receive anything, or it's somehow the underlying network layer is just sending like completely random data that isn't.
No, but in that case, the end-to-end will catch it, right? The solution 2 is always complete, because what it will do is that it will retry. Even the retry is time-bound, right? So after retrying for 1,000 times, it will say timed out. Go debug your network or something. So this is what I was coming to. So that does it mean that the lower level should never implement any functionality? That's not the point, right? Sometimes the performance may be impacted. One simple example I can give you is that in many of these communication links, people have figured out that oftentimes the errors are really simple. Only one bit flips, a couple of bits flip, right? So in this case, if you can, if a router receives some frame and figures out, hey, only one bit of that is flipped, and if it can correct that bit, right, then it can be blazingly fast than the receiver figuring out in the end that the CRC doesn't match and then asking the sender to send over again, right? So for performance, clearly low-level things matter. But what the authors were getting at is that don't try to over-engineer stuff at the lower layers, right? Do just enough for you to get the performance, but you don't need perfect reliability. It's a probabilistic thing. Even retry is a probabilistic thing. If, for example, your chances of a failure at a communication link, right, is 50%, right? If you retry 5 times, you can show that your probability of successful transmission is close to 1, right? But if the bottom layer, so what I'm saying is the bottom layers need not, the reliability of the bottom layers need not be like 99.99%. And also other thing is that when you add stuff to the lower layers, because the lower layers are common to many applications, you are needlessly asking many applications to pay. One classic example is encryption. Adding encryption at lower layers is an overkill because most applications don't need encryption. So yeah, data encryption is a classic example. Other things is that duplicate message suppression, right? That's also something that, if your network can do multipath route, like different multipath routing, and if sometimes when the sender accidentally thinks that the message may have been lost and it sends, it's possible for the receiver to get 2 copies, and in that case, the receiver might have to suppress one of it, and the question is whether that suppression should be done by the network or by the receiver. Also better done by the receiver, right? And in-order delivery is another thing. So, for example, if you know that the network can cause out-of-order delivery of packets, you can force each of the routers to reorder the packets, or you can do the reordering at the end host, at the receiver. There are cost benefits there, depending on which one you choose. So anyway, this is just the same argument. So basically, the paper is arguing that as designers, just there is when you're implementing something at the lower layers, a thorough cost benefit analysis should be done. That's the high level point. So basically, think twice before implementing some functionality in the network. If the host can implement the functionality correctly, implement it only as a performance enhancement, right? And do so without putting too much burden on the applications. So I would strongly recommend that you guys go and read the paper. It's a good paper to read. And I want you to, just end today's class with this question that, which among these things do you think sort of belong in the network? So whenever I say belong in the network, I'm really talking about whether you have to implement it in the routers, which means that whether you have to implement it in link layer or network layer, okay? So, which among these functions, right, do you think are today implemented in the network or link layer? Anybody can? Any link layer. When I talk about link layer, there are many link layer technologies, right? There's wireless, there's blah 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 blah. So, do you think any of the link layer technologies implement reliability? Yeah.
Shouldn't the security be like one of them? Like for Wi-Fi, there's passwords and stuff like that.
That is for authentication, right? It's not for reliability. So actually, you sort of Wi-Fi actually implements reliability. So because the wireless medium is very prone to errors, if you do it completely end to end, your performance will suck. So today's wireless link layer implements reliability. So if there is any packet loss or something, you will just resolve it at the link layer. So that's implemented in the network. Congestion control is not. It's very complex, right? So it's only implemented at the end host. Quality of service, there are efforts where people have tried to provide quality of service by doing reservations. And finally, security and firewalls. What do you think? It is implemented in the network. So many of the routers, like Cisco routers and stuff, they come with firewall, so you'll be able to configure it and do stuff. So that's all I have for this class. And so what I'll do in the next class is that I will briefly do a small walkthrough of Git. Some of you who may not know Git, I'll just do a quick, because of all the class projects you'll be using Git. So.